Hi, my name's Sarah Wielgosz. I will be presenting my work on characterization of neural ordinary differential equations for astrodynamics applications. So, to motivate this work, the high-level question that I'm interested in answering is how can we learn dynamics automatically in complex space environments? So, in space settings, our spacecraft experience complex dynamics due to perturbations from things like J2 or solar radiation pressure, or we might be in a low gravity environment where we need high fidelity dynamics. So, how do we do this? So this is where the field of scientific machine learning comes in. Scientific machine learning is a field of machine learning which combines physical laws with data-driven models, whether to inform models or to directly learn these laws. And we can improve model efficiency in doing so. So these models are really good for engineering and science applications. And the particular flavor of scientific machine learning that I'm interested in, especially for modeling unknown dynamics, are neural ordinary differential equations. And what are these and why are they good for our interests? So neural ODEs are special compared to other types of modeling methods because we actually learn continuous dynamics and we learn the vector field describing the dynamics of a system. So for example, take the two-body system here. We would actually be learning these underlying accelerations shown by the vector field. And some advantages of neural ODEs are we can use them for continuous time modeling, we can learn complex nonlinear dynamics, and we can handle irregular and asynchronous time sampling, which is particularly useful for our case where we get data streams back from spacecraft at irregular times that aren't necessarily lined up with each other. And it's clear that these are well suited for applications, but how are these actually trained? I'm going to give a brief primer, and it's not important to understand all the details, but I'll point out the key concepts for you to understand and be aware of. So, the goal of our neural ODE is to parameterize continuous dynamics using an ODE. And we parameterize this ODE using a function, which in our case is going to be an MLP. And of course, to train our model, we need a loss function. And what's really important to note here is that our loss function is a function of the integrated dynamics that are currently known by the model. For example, we might compare the integrated Cartesian state from some initial condition under true versus estimated dynamics. And of course, we need to calculate our gradients to make updates to our models. So to do this, we use the adjoint sensitivity method, and we first define adjoint as the sensitivity of our loss to the model's hidden state at time t. And we can now define the gradients as shown. And the most important things to note here are that our uh, dynamics of this augmented ODE actually control our gradients. So we have a gradient parameterized but yet another ODE, and we're integrating backwards in time. So how do we evaluate model success? There are two important quantities that we want to look at. And the first is the actual quantity of interest, which is our acceleration error. So how well are we learning this vector field? And the other is, of course, relevant for training, which is what is our loss metric as we are training our model. So in this case, we're going to use Cartesian state error, where again, we're going to integrate an initial condition under true versus estimated dynamics and compare the propagated values. So in order to demonstrate the potential of neural ODEs to learn unknown dynamics, we're going to show a proof of concept by applying them to two tried and true systems, our two-body problem and our circular restricted three-body problem. And we're looking at planar cases here, and all I really want to note is that, of course, two-body dynamics are very simple, while as the CR3BP is much more complex. So we want to test the ability of the neural ODEs to work on systems of varying complexity. And before I begin, I just want to give a little context for neural ODEs. There's one important concept called the length strategy. And this is where you have a model which you're going to train on first a portion of time series data to warm start the model. So for example, let's say we have this training orbit. We're first going to train on, say, 10% of the time series data from every trajectory in the set, and then the the whole trajectory. So this can improve model efficiency, and we can learn progressively and improve model stability. So with this in mind, we're going to discuss our efforts to train for the two-body problem. So we train on increasingly complex scenarios, starting first with a single orbit, then a simple case where we have low eccentricity in Leo, and then the complex case where we span from Leo to Geo and low to high eccentricities. And note that none of the model training parameters are of particular importance. Just note that we are using a length strategy of 10, then 100%, and we're using the same model architecture for all of these training scenarios, which we did because we thought, the dynamics are so simple that we should be able to use the same architecture for all training scenarios. And what we end up seeing is that for the single orbit, we overfit as expected. In the simple case, we're reaching pretty low losses as we hoped and low acceleration errors, less than 1%. But when we move to the complex case, this whole thing kind of blows up. So we're seeing loss on the order of about 80% in the Cartesian state, which is obviously unacceptable and renders our model useless. And here's just an example of the propagated circular initial conditions under these training models. And these are as expected, where the single orbit cannot generalize to a different eccentricity, but it does an okay job. And our simple model looks good, and our complex model is just totally unusable. So what's going wrong here? And we wanted to hunt down this issue in our model and figure out how to rectify it and why we're not seeing our model train as we wanted to. So to do this, we tried a few different methods, but I'm just going to boil it down to the two most important ones. And that is length strategy, which is kind of the most talked about in literature. So can we increment the amount of time series training data to improve our model training? And the other is segmentation. So can we segment each orbit into smaller trajectories, treat each of those as a unique trajectory, and kind of what happens as a result? So looking at the length strategy, let's look at a case where we're going to train on our complex data set. And for each training orbit, we're going to use a length strategy of 10, then 25, then 50, then 100%. And these are the associated losses. And what you can see is that the loss is going to increase proportionally to the amount of training data. So we were a little confused why this was happening. We expected to be seeing better training, which would be converging to lower losses. But what's happening here is, if you recall, this ODE defining the dynamics of our gradients is that if you integrate for time horizons that are too long, what happens is if you have an overly stable integrand, then you're going to experience vanishing gradients. So this is what we were seeing here, and our model wasn't learning any useful information. So to mitigate this, we segmented each of the trajectories in our training data set so that we would be integrating over smaller time horizons to hopefully mitigate these integration issues. And this was in fact successful, and we can see that our acceleration errors are now less than 1%. We see acceptable Cartesian state losses, and we're on the order of about 0.5% acceleration error, which was really promising. So I'm going to breeze through our two-body results a little bit, but shown here is the ability of our training on different data sets to generalize, and we see nice low acceleration errors, and we see that our model is predicting these trajectories well. And as expected, we see that our acceleration residuals are going to be higher if we train on just one simple data set versus if we train on the complex data set. And the simple data set is underestimating these accelerations. And now we're going to look at training on the CR3BP. So after we kind of identified this issue and that you need to segment your data, we were comfortable moving on. So we train on 4 increasingly complex CR3BP scenarios, starting with a single orbit around Lagrange point 1, then a family around Lagrange point 1, families around all of the collinear Lagrange points, and finally families of orbits around all of the Lagrange points. And like for the complex two-body problem, we segment these trajectories, and the results that we got are very promising. And the spikes that you see here are because we combined both a length strategy as well as the segmentation. So we see that our acceleration error is in fact decreasing and converging as we expect. And we see that we have kind of acceptable losses and acceleration errors, especially for initial results. And these will only improve in the future as we perform more model optimization. So in terms of what these results actually look like, as we train on increasingly complex scenarios and then test on other scenarios, we see that our model does a good job of predicting accelerations when the testing data set falls within the bounds of the training data set as expected, and we're seeing mostly sub 10% acceleration errors. And on the right, you'll see some of the actual trajectories propagated, and recall that the ones that might look a little bit wacky can appear so just due to long integration times, whereas the acceleration errors themselves look pretty good. And here's an example of some of the residual errors that we see for the CR3BP. So again, the blue is when we train on a single orbit. The red is when we train on families at all Lagrange points. And this is, again, as we expect, where our errors decrease as we increase the complexity of our training data set. So to conclude, neural ODEs show promise as a method to learn general underlying unknown dynamics in astrodynamic settings, and nuance is required in training, even in the cases of simple dynamics like the two-body problem. So segmenting trajectories is highly recommended, and this should be investigated depending on your use case. So in the future, we are going to focus on increasing our model accuracy and extending to more complex dynamical systems. Thank you.